Good morning, all. We'll be starting very soon. Just giving folks a little bit of time to get settled. Alrighty, I think we could get started. So welcome everyone. I'll let folks in as they start logging into the training, but really happy y'all are with us this morning. Next slide, Albert. So today we have Ventilation 101 with Albert Rooks and Eva Rooks from Small Planet Supply. Eva will be listening in today, but she is here. Next slide. Before I pass it on to Albert for this morning's training, I just have a little bit of housekeeping slides to introduce 3C Ren to anyone who is new to our network. So a little bit about 3C Ren. We are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties, working to improve energy efficiency in our region by offering free programs and services for building professionals and households. 3C Ren is funded by ratepayer dollars, which are collected through the public's good charge found on our utility bill. Next slide, please.
There we go.
We currently have 3 programs. Our first one being the Energy Code Connect program, which we offer industry trainings, regional forums, Title 24 consultation services called Energy Code Coach to help building professionals navigate the California Energy Code and green building requirements. And then our next program is our building performance training program, which we offer trainings on technical and soft skills related to building science, principles and systems for high performance building. And the last program we have right now is our home energy savings, which serves households that are historically underserved with free and discounted home energy upgrades. And with that, I'll hand it over to Albert to get us started with today's training. Thank you.
Great. Well, thank you very much, Itzel. A pleasure to be here with everyone today. It's fine to place questions in the chat, and Itzel and I will kind of check in and answer any questions as they pop up. My name is Albert Rooks, and I'm CEO of Small Planet Supply. And Small Planet Supply is a mission-driven company that really seeks to help designers and builders build really good, modern, classic design buildings, but buildings that use very little energy and really kind of pay attention to embodied energy. And so we hope to kind of help guide the industry forward into making buildings that won't really cause us problems in our own health and then the health of our ecosystem where we're building. I never really thought that I would find a subject like ventilation so interesting, but I do. I enjoy talking about ventilation, and I'm happy to be here talking about it this morning. It's a simple subject, but considering that we can't really live long without taking a breath, it's a really important subject. Doesn't matter what kind of project that we're working with, when we deliver a project with great ventilation, those who inhabit the spaces that we create will really feel it. We humans are sensitive to our surroundings, and we can feel when we have plenty of fresh air, just as noticeably as when we feel sleepy in a closed-air classroom or getting low-grade headaches from being overrun by noxious chemicals. So ventilation is really pretty important. We want to kind of understand who's here and can speak to kind of specific questions and levels. So we want to know a little more about you. And I think here's the quiz or the poll popping up there. So we'll wait a little bit and let you just pop some answers in and so forth. Thank you for doing that. Great. Well, so good morning to emerging professionals, students or young folks, builders, contractors, and all the others. I'm another. I'm not a builder or any of those other classifications. So welcome everybody. And just, as the questions pop up, feel free to put them in the chat. Great, thank you. Okay, we'll move along here. I think we've got one more series of questions, and we just want to maybe take a quick moment to understand maybe what your knowledge level is about ventilation. Is it a new subject? Are you a little familiar? Or are you ready to kind of take the stage and teach the class for me, and I can sit back and drink my coffee? Okay. Great. Some knowledge, a little bit, good mix. Nobody ready to teach the class yet. Guess I got to do it. Okay. Great. Okay, so thank you for that. And there's kind of our class mix. Nobody's stepping up to teach, so on we go. Okay, so we'll kind of keep moving, and as the questions come up, just let me know, and on we go. So course objectives are, let me get my electronics to work here for a little bit. Pop the poll off my screen. And so we're going to talk about ventilation. We're at the end of this course, we're really hoping that with changing codes and tighter homes, we can understand the need for ventilation and how that affects kind of these new homes that we're building. Project designs and clients will vary over time as ventilation becomes more important, because in these newer homes, it's more important. It's important to be able to discuss the 3 ways that we can ventilate a home and the factors to consider once you're starting to plan and design. And it's important for everybody on the project team, and especially the owner. And it's a way to kind of stay ahead of code and build a really good environment. So tighter homes do impact and are impacted by ventilation in a really big way. Homes are getting tighter. That's a great thing. There are lots of reasons driving the change. Some of them are environmental. Many are affected by energy. Other than energy savings, there's lots of benefits in a tighter home that we'll discuss. If you'd like to create a safe space where occupants can feel warm and comfortable, all of the research shows that homes are best when they're built tight and well ventilated. There's lots of reasons that we need to manage the airflow in a home these days. It's different than it used to be. We need fresh air to survive, but beyond simple survival, we need indoor spaces where we can flourish. We can flourish in the enclosed spaces that we create when we have systems that will control the indoor air quality within the ranges that are healthy for humans. In addition to supplying fresh air that's rich with oxygen, ventilation will manage the buildup of CO2, moisture, VOCs, allergens, molds. And these last 3 are harmful to us, to all of us to some degree, but they're really hard on certain populations who are more sensitive to these pollutants and can experience severe medical reactions, especially to molds and allergens. Ventilation helps us control these factors by both diluting, adding more fresh air to displace, or exhausting by pushing bad air out of the building. I love old homes. I live in an old home right now. And it used to be true that we never really had to worry about ventilation because the houses were so leaky that a gentle breeze on the home would push some air right through the building enclosure into the home and bring with it lots of fresh air. The homes were comfortable. They weren't cheap to condition, but the lack of air tightness and insulation meant that you could have plenty of fresh air and manage the building that way. These days, it's a little bit different, but in those eras of homes, old homes make use of a ventilation system that we don't cover in our course. It still has a given name. I don't know if anyone knows what that name is, but we won't make it into a real clue unless somebody's going to pop it in there. Okay, I'm a plain old, Edward says, I'm plain old homeowner trying to find my way through it all. Sarah says exhaust only. Nope. I'll save everyone the answer. The answer to this question is called adventitious ventilation. Adventitious ventilation is basically just a leaky home. It's the circumstantial airflow from outdoors to indoors through the leaks or unplanned openings in a building envelope. And Casey, yeah, exfiltration, yeah, but exfiltration is just kind of one direction, and adventitious is both kind of air coming in and air leaving. So Eva says like an advantage until you see your heat bill. Yeah, couldn't agree more. We've experienced that. In any case, that's what we have with an older home. It's adventitious and it's just leak. It could be wind flowing against the building envelope. It could be stack effect in a warm day, or it could be stack effect in a cold day. It's just a leaky building. And so the airflow is basically taking advantage of the leaks that it finds in the building. And airflow is just really driven by pressures. And as the pressures change, they just push through the leak points. So homes are getting tighter, and there's a lot of ways to make them tighter. And as we make them tighter, they do get more comfortable. Right, more insulation, less drafts, less overheating, less less effects of cold drafts in the north. I'm up in Olympia today. It's cold and rainy, and if I was in a leaking home, my feet would be really cold because I'd have that kind of cold draft in my feet. The effects of a tight home, managed along with some other factors, reduces the energy load and reduces the effect of weather and the impact of the outdoor. New homes are built tighter to improve occupant comfort and save on the amount of energy needed to heat and cool the home. It's getting easier to build tight with the addition of specialty tapes, fully adhered membranes integrated into the sheathing like Zip and other products, liquid applied membranes, and the list goes on. Our company, we've handled all of those materials, help builders build down to 0.6 ACH 60 and lower. Super easy to do that these days. With less air coming in through leaks in the building, there needs to be a thoughtful plan on how occupants get fresh air, because we've really just kind of cut off the adventitious airflow, as you say. We don't want to be in a situation where the industry has gotten really good at air tightness, but due to a lack of ventilation knowledge or ventilation practice, the occupants are starved for fresh air because the building is built tight and we didn't add any airflow. That's partly some of the reasons some of the codes haven't really changed. If you're writing policy, my experience up and down the West Coast is it's a bit tricky to really push that air tightness unless you've got a strong ventilation practice and industry and knowledge behind it. So we're slowly kind of ramping up as a building community, getting to that point. And then other things are going on. I never expected to have to deal with this in my career, but we know what this picture is. Doesn't matter where we are on the West Coast, smoke and fire is the new reality. We sure wouldn't want a light breeze pushing this smoke into an old leaky home. An airtight building, good ventilation with filtration will let us manage the worst of this. The better the ventilation system and its controls and its filters, the more comfortable our occupant will be. Smoke is a particle. It has a size and a corresponding filter that allows air to come into the home while leaving the smoke outside and captured by the filter medium. Even if we consider that we can live with less air coming in, We still need to exhaust air to manage moisture from showering, buildup of VOCs, and buildup of allergens. The smoke that I make from, well, yeah, including the smoke that I make from burning a frozen pizza. And I always say that because even cooking a pizza is simple, but I managed to kind of create some smoke doing that myself. And that smoke needs to go out, right? It's big, nasty blue smoke. We need a ventilation. We need ventilation even when we don't think that we need to. So ventilation manages a lot of factors. Smoke is just one of the many elements that we need to consider in assuring healthy indoor air quality. But as we spend more time indoors, we need to manage the indoor air quality of all of our spaces. That's the purpose of ventilation, to manage the indoor air quality when homes and windows and doors are closed up. Without it, the space begins changing in ways that are really unhealthy. The chart that we're looking at lists some of the factors that begin to drive the conditions by the home being occupied when it's closed up. A ventilation plan is designed and installed to drive it back into the optimal range shown in the middle. The light blue optimal range or optimum zone is the ideal range of relative humidity in the home. We can adjust this by increasing or decreasing the ventilation flow rate. As we get deeper into advanced ventilation workshops, we can find that the simple laws of physics will help us manage the relative humidity of our indoor spaces. Ventilation is a lot of fun the farther you get into it. And so, if you have the opportunity of taking an advanced workshop, I do that. Essentially what happens when we try to manage into that optimum zone, we're in a situation where we as humans in the building, we're constantly creating some moisture. And so we can set up ventilation to kind of understand maybe what those moisture loads are and set up an exhaust rate to keep moisture leaving the building. And depending on where we are in the environment, then we can deploy some heat or moisture recovery with some heat exchangers or energy enthalpy exchangers and start managing the moisture load that way. Super, super cool. It's really effective. It's really how we create some really special spaces. But there's also pollutants, right? It's not always just outside and inside, it's a mix of materials. When you're outside in normal conditions, there's a constant flow of fresh air to dilute the pollutants. When you're inside with no ventilation exchange, the lack of fresh air means that you're trapped in with all those internal sources of chemicals and pollutants that you brought into the home. You may not even realize you're bringing them into the home. These include off-gassing from building materials and the original furniture, chemical from cleaners, combustion gases from cooking or heating if we're using combustion to do those tasks, pet dander, mold spores, moisture in the building can be a big factor. It can be a pretty long list. There's always something going on. Good ventilation is how we ensure the pollutants that we create or bring into our home can get back out. So, and it's always worthy to pay attention to the effects they have on our body. We're all occupying spaces and we're creating spaces for clients. And so we all have a role in kind of understanding maybe the issues and creating some strategies to solve them. Our bodies are very sensitive to the indoor environment. The link between common indoor air pollutants such as radon, VOC particles, carbon monoxide, Legionella, all of these affect our health, and they're really well established. We know how they affect us, and it's not in a great way. So we really want to manage it. Health effects associated with these indoor air pollutants include really short list, just the high level topics of these. It's a long list, but I'm just sharing a short portion of the list. Irritation of eyes, irritation of nose, irritation of throat, headaches, dizziness, fatigue, respiratory diseases, heart disease, and cancer. And I think I'm seeing some recent statistics that talk about health effects from environmental air quality, indoor and outdoor, is now kind of on the rise as as becoming a global leading cause of death. And so, really, we've got some tools to manage that. So we'll keep looking at this. So here's a really cool home. Know this home, been in this home. It's on the Monterey Peninsula. The home was built in 2016 to be a healthy home. Great care was taken by the owner in material selection to avoid using materials and finishes that would off-gas harmful chemicals into the home. Even though the owner has a long history in both the building materials industry and sustainability, it was impossible to create a home that didn't introduce harmful VOCs into the air. And so, I kind of know who was driving that project, and they are really a pro at selecting and evaluating the building materials going into it. We haven't even gotten to furniture. So originally it's kind of this low green level, and it's way below the World Health Organization recommendation. Things are looking good, but you shut off the ventilation system and close up the home for 2 days, and the total VOCs spiked from the very low level to 3 times the WHO recommended threshold. And these are real numbers. This is based off of monitoring VOCs off of this home. This peak is very much what a normal home being built to today's standards would look like without a working ventilation system. Most homes that we're building today are, they're a little bit light in their ventilation system, and we'll get to what ventilation systems we're seeing in the market today. But they're not that sophisticated, and so hence we're talking today. So once the ventilation's turned back on, look at that. VOCs drop, they drop fast, right? Because the ventilation system in this home, I think, is set up to run 0.5 air changes an hour. We're going to look at air changes an hour. That just means that half of the air volume in the house turned over in an hour, right? So that's why it was such a precipitous drop, is we've got a ventilation rate that'll just take half of the air in the building and send it out within 60 minutes. And that quickly affected the quality of the building. The airflow quickly falls down to under the World Health Organization threshold and becomes really back into a healthy space. Now we can really see what happens when we don't ventilate a tight home, even when it's built with the most care and material selection that someone can apply. So we'll take a quick pause. Questions, comments, any need to backtrack on anything? Okay, all good. We'll keep going. Okay, so now that we understand, some of the health effects of ventilation and maybe what our goals are to manage the indoor air quality, let's start looking at the systems and the way that we can, what kind of tools we have to work with that. Edward asked if you would add a ventilation system to an old leaky home, and yes, Edward, I would, and I did. And it has a really strong effect. I added the far right-hand picture, a balanced ventilation system to a very old leaky home, balloon framing, Northwest 1938, 2x4 construction, all the wrong things if you look at it today. And we really started looking at some air tightness, and just the way it's set up, air tightness is pretty challenging on that. So it's a really it's a very leaky home. We put in a balanced ventilation system, and we actually monitor the airflow and the air quality. It's had a really strong effect, and we've lived in both well-ventilated homes and very poorly ventilated homes on kind of the evolution of our business. And my wife and partner, Eva, will pretty much not live in a home without a ventilation system these days, because we both felt that. So 3 basic types: supply only, exhaust only, and balanced ventilation. The middle one's going to be pretty familiar with everyone. All of these types of ventilation designs have their own sets of strengths and weaknesses. So we'll take a look at each one and see what fits in the homes that we build today. So supply only. Fresh air supply only is fresh air supply provided, comes in from the outdoors intentionally through some ducting, and into a central duct system as a standalone strategy, or with heating and cooling systems for distribution throughout the home via a central air handler or duct system. I've lived in some, maybe they're older units now, but it was kind of that approach where you'd have a central fan on a timer, and basically that fan is either in a supply mode or it's in an exhaust mode. There's two different reasons. In this case, it's supply mode, right? So we're just bringing in air across a fan on a schedule and pushing it into the home. It could be into one spot or it could be into multiple spots. We're just pushing air into the home, and that's about all we're doing. And so maybe the pros of the supply only: it's low cost. All you really need is a fan and control, and maybe a filter these days, of course, and some simple ductwork. Where the heating and cooling system is forced air, the air is typically introduced into the return duct ahead of the air handler. So the outdoor air is filtered before it goes into the ducting system and is distributed. Outdoor air will also be conditioned when it's introduced to the space conditioning flows as that system is on. If it's not on, controls are integrated into the system that steps the air handler back. It runs at a lower flow, doesn't add any heating or cooling to it, but it's just basically supply only. So it's pretty simple. It's easy for an installer to do, and it doesn't really cost a lot of money. The downside of supply only is supply only systems tend to pressurize the building, as there is no exhaust pathway to relieve the pressure other than a bath fan or range hoods. When the doors are closed and the pressure seeks the next lowest resistance pathway, which could be through the building envelope, and as air passes through the envelope, moisture is carried with it, because we're always creating moisture in there, and condense onto a cold surface during the heating season, right? And so California's got, 13 climate zones. We've got all these different conditions. And as we're pressurizing a building, and that building is creating, or we're creating moisture inside that building, and as we push it out, in some conditions, that moisture is going to come into contact with our building structure, and in cold conditions, it'll wet. And wetting in the building envelope can definitely lead to mold growth. When the ventilation air is distributed through a forced air heating system, heating or cooling, the ventilation flows are very small compared to the amount of air needed to carry heat energy to warm outdoor rooms. Warm rooms. The low ventilation flows are so small that they kind of get lost in the ductwork, because the ductwork's really sized not for ventilation flows, which are really small, compared to heating and cooling flows, which have to be really big, and so the ductwork is big. That ductwork that's sized for the high flows to distribute the warm heated air or cooler heated air means that the ventilation air will typically only reach the nearest supply registers, right? So if you have a big, long rectangular home and the air handler's in the middle or one side or the other, it's only that fresh air is just going to get pushed out of the nearest registers. So it won't make it to the ends. And often in the ends, that's where the bedrooms are.
Hey,
So
Albert,
yeah.
sorry to interrupt. We have a question from Sarah, and
Oh,
she's
yeah.
asking, what are those icons showing the air leaving the home?
Oh, so in some, thanks for that. In some building structures, there are just ducts, like in windows, or just little round ducts where we can pressurize the building. And rather than having no exit pathway, those are exit pathways that we provide. I've seen a lot of multifamily buildings with their window systems building in fresh air ducts that can be an intake point or an exhaust point. So those are just intentional exit points. Does that make sense? Okay, you're welcome. With a supply only system, odors and allergens can get pushed around the home and be redistributed from room to room. And so, supply only kind of gets us there, but it has some issues with pressurizing the building, not understanding where the moisture goes, and then of course we're bringing in constant airflow, and not really getting it fully distributed to all the rooms involved unless we build out a rather substantial duct system that's sized just for ventilation airflow rather than heating and cooling condition. So now we'll also take a look at exhaust only system. So exhaust systems are probably the most common. This is really what we're seeing. This is kind of where the code's built around, because it's kind of our first foray into ventilation. So fresh air exhaust systems use one or more exhaust fans to expel air from homes, which introduces fresh air to be pulled into the home through any available cracks or holes in the construction assemblies, and they could be cracks or assemblies, or they could be those intentional ports that are placed in the building envelope or in the windows or other fenestration. Typically, bathroom exhaust fans are used along with integrated controls that ensure adequate outside air to meet design requirements. When we start looking at those bath fans, kind of the new fans are built around codes and ASHRAE standards for sound, and then are advised on kind of the length of run. If you push the button, it'll run for 20 minutes or a number. There's a lot of options there, but that's really our ventilation system, is the bath fan and maybe the kitchen range hood in an exhaust only ventilation system. Or it could be that whole house fan also that would just doesn't really have a makeup air pathway. It's just going to be pulling air out, and possibly it might have a makeup air pathway. So mostly in kind of most of the buildings that I've seen that don't have a more detailed planned ventilation system is exhaust only, typically using the bath fans, and that's how we meet codes. The pros on that, how we got there, is that it's pretty inexpensive. We're just buying some bath fans. They're simple to install. Everybody knows how to use it. They have their own built-in controls, and they will dilute and remove contaminants depending on kind of how the home is structured and laid out and so forth. And it's possible to reach the ventilation minimums, the code minimums, by adding a simple central fan. And in that case, we'd have a central fan and exhaust fans in the bathroom. Exhaust only will dilute and remove contaminants from the home. Exhaust only will not push internal moisture into the building envelope. So that is kind of a pro, right? We'll be pulling through the building envelope rather than pushing through the building envelope. The cons are pretty significant, certainly to me. On the downside, this strategy uses the negative pressure created by the exhaust fans to pull fresh air through the envelope voids. Typically, I don't actually see a lot of buildings with these intentional makeup ports, either at the windows or integrated into a building envelope. Usually, they're just pulling through the building envelope, whatever the defects are. And if no one's really watching air tightness, and the air tightness is common, from 5 to, or maybe even 3 to 7 air changes an hour, then that's what it's really pulling through. The quality of fresh air received by the occupants is only as good as the building envelope voids that it passes through. As the building ages, deposits of moisture and dust from the infiltration will accumulate. The air passing through these accumulations can definitely pick up harmful toxins and create unhealthy living conditions. This is especially hard on sensitive populations. Homes with wood stoves or other combustion devices can create really pretty dangerous conditions when subjected to negative pressures. The combustion gases like carbon monoxide can be pulled from the combustion chamber into a home at a steady rate. this is very dangerous. This happens as you make a tighter building, then we're looking at what the lowest possible draw pattern or pressure regulation for makeup air, and that could be coming through a combustion appliance, right? If it's not very well sealed or installed properly. Deaths associated with carbon monoxide poisoning are far too common. And the correction for this is to provide makeup air directly to the appliance. We recommend using extreme caution when the combustion is used with exhaust-only system. In exhaust-only, it's difficult to add filtration to most exhaust-only systems, so you really can't. It's not very easy to manage those outdoor pollutants as they come into the building. A little easier on supply flow, right? So finally, we'll take a look at balanced ventilation system. This is absolutely my favorite one. This is what we would recommend.
Sorry, Albert, to interrupt. We have 2 questions in the chat.
Isabella, are there certain climates in which you might prefer exhaust versus supply? Boy, that's a tough one to answer. I'm gonna say I'm gonna prefer balanced. Exhaust versus supply. They're both really not great. They both really put pressure on the building envelope. And I don't feel expert enough to understand in a cooling climate what that would really mean to the building envelope. In a heating climate, it's just pretty bad. You wind up with a really nasty building envelope because as that moisture gets pulled in through the building envelope, it does condense and it starts building up because the first pass, kind of the sheathing layer and the structural layer usually can be pretty cold, and that's when it'll start condensing. So I don't like either. Balanced ventilation is really the best trick, and we'll talk about that next. Edward, sorry for the intake only systems. Could you explain again the issue of appropriately sized ducts, i.e. not good to just go through existing HVAC ducts? So great point. Okay, so here's how you have to realize my goal is to build some really, really nice ventilation systems. And when I look at fresh air, and we're going to look at some slides later in the deck that talk about bedrooms. And Edward, it really kind of comes down to bedrooms. So if you say a ranch home, and I gotta kind of pick some kind of shape, right? So single level ranch home, because it's really easy for us to imagine. And we'll say it's forced air, and we're going to supply fresh air into the return plenum and then push that fresh air into that duct. If it's a couple thousand square feet, maybe 2,500 square feet, because that's an easy number. If we look at most of those duct systems, they're really pretty big. The return plenums are 20 by 30 inches, big square with a big filter. And then as we branch out across the home, we break down into, things that are more like 8 by 10 ducting, big kind of rectangles, because air isn't very dense, right? And so if we want to heat or cool, we can't. It's not like water where we can heat a little bit of water, and that water is so dense and carries such a high load of energy that we can just kind of push that water into a radiator and just get a big mass of heat off of it. With air is not very dense. So when we heat it, we can only heat it so high it's somewhere around 120 or something like that. Because if we overheat it, that's when you start burning dust, right? And you can kind of smell that. So you can't get it too hot like you can with water, and it's not very dense. So the only way you can move a lot of heat is to move a lot of air. With ventilation, we would use 1/10 of the amount of airflow that we would use for heating or cooling. So when we use 1/10 of the amount of airflow in these really big ducts, there's just no pressure against that airflow. And because it's always looking to kind of leave the duct system, because it's kind of getting pushed by a fan, getting channeled down this duct. And the first opening where it can go to a zero pressure environment, like a room, it'll go. It won't continue down the duct. And so if you got that long rectangle and you're either in the middle with your air handle or one of the ends, it's just going to leave the soonest port. And because it's 1/10 the amount of airflow, that room, wherever it's going to, most of it'll go there, and that room will be really fresh, but none of the rest of the duct run won't get any airflow, right? Because it's just the way that works. So hopefully that answers the question. And as we get into room airflow, we can kind of come back and talk about that a little bit deeper. So so now let's talk about the balanced ventilation systems. So we'll take a look at balanced ventilation. Fresh air balanced systems supply and filter outdoor air, because we're bringing it in from the outdoors. We're bringing it in from one connection to the outdoors, and it's simple to put a filter there, while exhausting an equal amount of indoor air back to the outside. So it's balanced, right? We got 100 CFM coming in, and then for that 100 CFM coming in, we've got a matching 100 CFM leaving. And so now we're going to actually start thinking about kind of where the fresh air is coming from and where the fresh air is leaving from. And we'll look at it here and then some later slides. But this type of system maintains a neutral balance in air pressure that minimizes moisture risks and optimizes the mixing of the air. These systems are often equipped with a heat and moisture exchanger. That's an option that optimize the energy efficiency and the comfort. This is achieved by exchanging heat and moisture between the incoming air and the outgoing air systems, and especially when there's a high temperature differential, either heating or cooling, right? Because we've got on one side of the flow has got heat and the other side of the flow doesn't have heat. So an exchanger will just kind of move the heat from one side to the other. And if the goal is cooling, it's the same thing. We're just kind of working on opposite ends of that spectrum. And that's more of an advanced workshop where we start working with heat exchangers. So balanced ventilation captures the heat, or balanced ventilation with heat exchangers does capture the heat before it leaves the home in the winter, or the heat before it enters the home in summer. So we can wind up getting a thing called an HRV or an ERV, and it has the fans, and it'll bring fresh air in and exhaust fresh air out. And then in the middle of that appliance, it does have a heat exchanger. It's simple to kind of talk about. There's companies like ours and others that will help you kind of understand and size these things, but that's essentially it. We've got balanced airflow, so zero pressure differential on the building, and then we can also add some heat exchanging onto it to kind of lower the energy load and kind of maintain their comfort. Additionally, it'll capture the moisture before it enters the home in summer and the moisture before it leaves the home in winter to keep the home from drying out, which is another thing which we are going to talk about here. And you can, if you get the opportunity to kind of attend a more advanced workshop, we go into these subjects in depth. And today, with this workshop, we'll definitely talk about them, just not to a full expert level. So, pros for balanced ventilation. Balanced ventilation delivers really the best conditions and improve the health of both the occupants and the building envelope itself. In a big way, building envelope included. By keeping the building in a balanced state, there's no positive or negative air pressure across the building envelope. The fresh air enters through a dedicated supply intake, and the exhaust air is pushed out through an exhaust grill. Balanced systems are typically always on. They're not turned on and off, kind of like a bath fan. And the same amount of airflow entering and leaving continuously ensures that there's plenty of fresh air for the occupants, while the stale, moist air is exhausted 24/7, which is really helpful for the building envelope, especially baths, because we've got to maintain the baths because they're always a constant source of moisture. Since the system is sized for the home and controllable, conditions like relative humidity can be managed by the ventilation flows to keep the conditions within the healthy zone. So all we got to understand is, as we get deeper into it, if we understand maybe moisture contribution, respiratory contribution, how many people are living in the home and exhaling and creating CO2, we can understand those numbers, and we can set fan rates that will kind of keep it within that blue optimum zone when we were looking at kind of the humidity metric. And then also same thing applies to VOCs. Ductwork can be run to all the rooms and can be used to supply or exhaust the room. Since the system runs continuously, it can replace the standard bath fan with low continuous flow rates rather than the informal spot flow. That's a big deal. There's really, really good numbers on that side. The dedicated fresh air supply can be filtered, which can offer much better conditions for all the occupants. So the positive, the pros are really quite substantial. We'll talk about the spot flow in the bath in a later slide, and kind of look at how that works. And the cons, there aren't really any cons other than cost. So you've got two flows. You can actually add energy recovery. You can duct it all the way through the home or just partially duct it, but you get a building envelope that's not going to be passing any air infiltration or exfiltration, right? Because there's zero pressure, even when there's wind flowing or stacked effect. The ventilation system is a mechanical system, and so it'll really kind of overrun or actually replace the effects of infiltration, exfiltration, stack effect, and things like that. And then Eva put in a comment there, Albert, if you use an HRV or an ERV that has high efficiency, wouldn't it end up still reducing energy costs? Absolutely, it would. That is essentially the effect of Title 24 and anything energy modeling, because if we can have a fully intact and insulated building envelope, the insulation is to a degree, and that kind of contributes to what the energy load is. The ventilation part of that is basically the hole in the envelope. So if we seal up that hole in the envelope, because there's always going to be airflow in and out, and if we seal up that hole by putting a heat exchanger in the airflow and harvesting the energy that we created in the space, and then instead of sending it back outside, and then replacing it with unconditioned airflow, we kind of retain that energy and we essentially recycle it, which means we just don't need to create more energy inside, and we don't run into the circumstance of overheating in the summer. So there we go. So cons on the balanced ventilation really aren't any. It's really about cost, complexity, and design. It's really easy to design these systems, and so we can do that. So little quick question: what type of ventilation is not covered in this course? Balanced, supply, exhaust, or hyper. And I have no idea what hyper is, and hyper is the answer. We'll save everybody the trouble of answering that question. And so at this point, we've kind of covered the three types of ventilation. We've had a few questions. If there are any more, I'll take a pause from my coffee, which is way too strong this morning, and answer any questions that anybody has. And when we're ready to move ahead, we will move on to room-to-room distribution and talk about that. Okay, quick pause, and we're going to be off and running. So now we're looking at kind of how we work with these systems and how they affect room to room situations. So taking a step back, we solve the indoor air quality problems with one of the three types of ventilation system: supply, exhaust, balanced, not hyper. But since there are many rooms to serve, the ventilation system is only as good as its distribution system. The distribution system is the ductwork that carries the fresh air supply and the stale air exhaust. Let's take a look at the common distribution systems of all three. Homes vary, practices vary over time, and so we just kind of want to interpret this as I see buildings and as you see buildings. In supply only, there are two typical distribution methods of: one, a fan that dumps fresh air or fresh outdoor air into a central area with very limited ductwork. This tends to overpressurize the building, and the fresh air follows the building leaks, which are not necessarily where you want the air to go. It's just where it's going to go because it's always seeking a kind of that next level, zero pressure environment. So it follows the path of least resistance and may not pass into bedrooms whose doors are closed, leaving sleeping occupants with lots of CO2. We're going to look at CO2 here in a little bit later, but we'll be leaving those occupants with CO2, but no fresh air, right? Because there's not really a way that that air is going to get pushed into the bedroom unless most of the leakage is in that bedroom and it passes kind of under that door. So method two is fresh air is dumped into the return plenum of the forced air heating and cooling system. While these systems are ducted to the proper supply points to heat and cool the rooms, the air handler, when in ventilation mode, not in heating or cooling mode, runs on its lowest speed, right? Because we only need roughly 1/10 of the airflow for ventilation needs rather than heating and cooling needs. The low speed fan pushing air into ductwork that's sized for high volumes heating and cooling flows will only deliver fresh air to the nearest points, and only those points with less pressure than the other points in the distribution run, due to how close they are to a building leak, open window, or other way out of the room that they're serving. So you could find much of your fresh air going into the laundry room and exiting through the dryer vents, since it's a 4-inch diameter hole in the building and can pass directly through the dryer, or other penetration. So that's, and when those exit paths are always available, they wind up relieving the positive pressure built up on the building in a supply flow. So we do get air into the building. We just don't really have a lot of control of where that air goes in the building because we haven't built a system to supply that control. Exhaust only. As we saw earlier, exhaust-only systems use the negative pressure created by exhaust fans to pull fresh air through the envelope voids or other openings, and the openings may be intentional or unintentional. The quality of fresh air received by the occupants is only as good as the pathway that it passes through, and quite often that is the building envelope itself. Exhaust-only systems don't have a distribution ductwork, therefore there's no predicting how much fresh air a room gets. It's dependent on the amount of negative pressure the room is under and the intentional or unintentional supply points. There we go. Bedrooms with closed doors will only get fresh air if there's an opening for the fresh air to enter the room, and the pathway through the undercut of the door has less pressure to overcome the other pathways available, right? So we undercut the door, that creates a pathway, and the pathway only works as well as the rest of the system, and the pressure effects are kind of treating that space. This makes it difficult to control the room's CO2 levels when conditions such as outdoor air temperature or a noisy street causes the window to be closed. And so that happens, right? I mean, a lot of people, they're practiced to sleep with the window open, but we can't do that all the time. And you know, we're coming into a future where sometimes we really don't want windows open. So negative pressure also affects the rooms, including the kitchen and baths. While the exhaust ports of range hoods and bath fans have flappers that will close when the fan isn't running, the flaps don't necessarily seal the opening. The negative pressures will act on these openings and pull outdoor air through the exhaust ductwork across the flapper. The air coming through these can be unhealthy. Since there is flow into the room's airflow to the rest of the home following the negative pressure pathway from the pulling fan. This pulls all the moisture and cooking smells through the home and finally out through the fan exhaust points, wherever that could be. You know, it could be in a kitchen, it could be in a bath, and baths with bath fans tend to get used more often than range hoods and cooking. So it'll always kind of head towards whatever that exhaust point is. And in exhaust only, that's going to be typically bath fans and maybe a central air handler. And so the bedrooms still are really not served and they're really not managed. And bedrooms are where we spend a good portion of our lives and where we're supposed to rest and recharge and things like that. And so managing CO2 and VOCs and other contaminants in bedrooms is really, really important. Right? Our home is supposed to help us thrive. It's supposed to support us. And getting a restful night's sleep with healthy oxygen levels is really important and part of the function or part of the way we get a good night's sleep, I think. Bedrooms with no fresh air distribution are really a problem. With a window open, there can be lots of fresh air, but there are plenty of times that leaving a window open isn't a viable solution in many, many homes. Aside from urban noise, the energy penalty alone often defeats the efficiency sought in creating an airtight, insulated home. The envelope efficiency measures finally come together and are really effective when we have fresh air distribution to bedrooms that allows for windows to be closed when it makes sense to have them closed. When bedroom doors are closed at nights with occupants sleeping, the CO2 levels spike to unhealthy levels as seen in this study of 22 homes in Vermont. So heating climate, same thing applies in a cooling climate too, depending on where we are. But this is, I see data like this all the time and across many sources. The recommended level of CO2 while sleeping is about 1,000 parts per million, right? So 1,000 ppm. In this study, the first night of the study shown in green is near this level, with some homes peaking at around 1,700 parts per million. The first night had all the bedroom doors open, and the results were, while over the recommended levels, are passable, right? So that first night's looking okay. Night two, totally different story. Night two, shown in red, has all of the bedroom doors closed. The CO2 spikes to an alarmingly high level on night two, and it's obvious that most of the bedrooms don't have any source of fresh air without a window or a door open, right? So this is kind of the reality of many, many homes. And you can see in night two, right, there's some really, really high peaks and a lot of high peaks, but there's still some lower stats because all homes are a little bit different, and some could have another way of kind of driving that air, but certainly the ones that don't have a way of driving that air, boy, we see some really negative results. And then night three, we open the doors again and everything calms down. Looks like night one. Night four, we close the doors again, and we get pretty much the same results as night number two. So really we have the option of of really kind of treating this. But in addition to CO2, there's other contaminants that we're really trying to manage, right? Because ventilation is really the way that we can kind of push out some of those VOCs, moisture, molds, things like that. So CO2 is not the only problem. Remember that part of what fresh air ventilation does is to dilute the accumulation of what we bring into the home. Even homes that are built with great care to not add a lot of off-gassing and building materials, we wind up bringing things in. Those off-gassing conditions exist, and the lack of airflow and the effect of corners and condensation on walls or condensation in walls can really kind of add up to some harmful effects that can be solved by ventilation. We can't really rely on the dilution effect of ventilation without a fresh air distribution system to provide the airflow. So once we put that in, we can start managing these things. And if we don't put it in, we can't really manage them. So while at the start, it's about getting air in and out of the building overall, as we get deeper into it, we find that it also really matters where we get the air to go and where we're able to pull it out of. If we really want the benefits of ventilation, we'll need a ventilation system with room-to-room distribution. So let's take a look at what that looks like. Balanced ventilation with distribution is really the one I like. It's what our company works with. It's what I work with in kind of my all my work around ventilation. Even when we're doing energy recovery, heat recovery, or adding conditioning onto it, it's really balanced ventilation with intentional design distribution. It solves all of these problems and gives us the best shot at creating a healthy living space in all conditions for all health statuses, including the young, aging, like me, and very sensitive. Balanced ventilation uses a supply fan and an exhaust fan to flow fresh air across the whole building in a constant flow. Bedrooms and living rooms receive a constant flow of air. Baths, laundry, mudrooms, kitchens are constantly exhausting stale air or moist air. And with a steady supply flow coming in, the air washes from the supply points across the transitional zones, right? That yellow, in this illustration, that's the yellow hall area. So positive in bedroom and living room, pushing across the hall and getting kind of pulled into that kitchen and bathroom configuration. The two fans are balanced and constantly running, and the amount of steady flow will help keep the home's relative humidity into the optimal zone. It'll also dilute the buildup of VOCs and other contaminants and provide lots and lots of fresh air for the people in the home. It works best with today's newer, tighter homes and can be filtered to manage both normal and the extreme conditions due to smoke that we find in a changing climate. So in this circumstance, newer, tighter home, balanced ventilation with room-to-room distribution, which just means that we've got some ductwork that's sized for ventilation air rather than heating or cooling air, right? So smaller ducts sized for that 100, 120, 180 CFM flow that we need in that particular building, which is driven by the size of building and the number of rooms, right? Because each room would want some value of airflow into it, airflow pushing in or airflow being pulled out. And so we look at that, we create a design and a plan on how to deliver those numbers. And when we deliver those numbers, it is kind of this cascading effect, which is kind of what it's called, where the fresh air comes out of the supply points. It's come across a filter, so we filtered out kind of the outdoor particulates into the supply flows, creates positive pressure zones. Those push into kind of the neutral pressure zones. And it could be many different shapes of houses. It could be 2 floors. There's always a way to work this out because we'll set up a matching negative pressure zone in 1 floor, 2 floor, 3 floors. Doesn't really matter because the airflow will go from positive across neutral to negative and get pulled out on negative. Everything will stay in balance. And that means there's nothing coming through the building envelope because there's nothing needed to come through the building envelope. And we reduce the effects of stack effect because we're managing the airflow by design and by fan power. How are we doing on questions? We seem to be doing well on questions. Okay, so we're kind of coming into the tail end of this. So questions are always going to be fine. We're a little over an hour into it. So here we go. Okay, so here's what we think about when we're starting to plan for a ventilation system. Like many things in building, it's a team sport, and there are other team members out there that are definitely available to help you with this. But not everybody has the same skill set. So let's talk about this for a little bit, because even I'm continually surprised that people in the HVAC industry don't really think about this. Certainly to kind of creating these really well-designed ventilated spaces. So first question is, how much ventilation do we need? And so airflow is measured in many ways. The most common way is cubic feet per minute, or CFM. Saves us from liters per second and other measurements that we see in some of the European equipment and things like that. So CFM is a nice, simple matrix, and it's just cubic feet per minute. So one air volume, 12 inches high by 12 inches wide by 12 inches deep, one cubic foot. The flow measurement is used as the guide to determine how much flow is needed, and how much is kind of driven by two factors, by supply rates and exhaust rates. We have need for supply and we have need for exhaust, and they're really two different things. So we're going to kind of try and harmonize those two different things into something that makes sense to us. So people need fresh air to live and thrive, and therefore the first how much question is the supply rate. And it's based on how many people are living in the unit, because it's really about people and fresh air and oxygen and replacing CO2. It's figured in a number of ways. The most common measurement for supply flow is to size a fan to provide greater than 15 CFM per person that will be occupying the living unit. 15 is kind of small. There are other numbers to use. Let's just say that's the smallest one we'd probably use. In certain circumstances, it can also be set by a large enough fan to handle the anticipated flow requirement. So maybe a high side flow requirement, and operated by adding occupancy or CO2 sensors that will kick a fan on to supply air based on the actual occupation of the home as measured by the CO2 level, right? So in that case, we're using CO2 as kind of a proxy to tell us how many people are in the home by understanding what the CO2 level is, which increases as more people come in and breathe. There are some variables in this method that are best evaluated by a ventilation expert, but the upside is that the ventilation system can run at a lower rate when the space is not occupied. This will reduce the energy penalty. And there is provision in the California Code and Title 24. Quite sure about the code. I don't work in Title 24 quite often enough, but this demand response or demand ventilation is a thing. It's a normal thing. Our company just brought in a new unit from Europe that's entirely demand response. And so on the supply side, rather than saying, well, we've got a 1,500 square foot home and we imagine there'll be on an average 3 people in it, maybe 4 people in it. So we could kind of take a base rate of 15 CFM times that number of occupancy that sometimes will be there and sometimes no one will be there. A demand system will just look at CO2 because CO2 is a number that we want to manage, and it'll just run the fans based on what that CO2 level is. And when it starts climbing, it'll run the fans more. And when it slows down, it will run the fans less. When they run the fans less, even with the best heat exchanger, HRV or ERV on the market, there's always a loss, and we're always consuming fan energy. So when you really think about it, if you have the opportunity to not run the equipment, then and nobody's there, then you want to take that opportunity because it won't. You can set a base rate and kind of manage the VOCs by a very, very low base rate and just going to push those out. But you don't have people in there, so it's pretty easy to kind of keep it healthy from a CO2 perspective. So in any case, moving along. Second rate that we're going to manage is the exhaust rate. And it's driven by how many bathrooms are in a unit. Certainly driven that way by code. Each bathroom is required to have an exhaust flow. These rates are on continuous flow or intermittent flow, like a bath fan that turns on and off. The minimum rates for intermittent kitchens and baths in an exhaust-only applications are exhaust only. Kitchen range hoods, 100 CFM minimum fan. Bath fans, 50 CFM minimum bath fan. And the bath fan's controlled by a switch. So it's not going to be running all the time. It's just intermittent. Okay, so baths with continuous ventilation and no bath fan, just continuous ventilation, only need 20 CFM for continuous exhaust flow. And there's some interesting numbers. We'll just pause here for a minute to look at this, because in my work, people often stumble. Like, okay, we're building a new home and we're not going to have bath fans. We'll say, don't have bath fans. Bath fans are not great. I'll save my editorial thoughts on bath fans. And we're going to suggest using continuous ventilation. And so continuous ventilation at code minimum, and it's a good number, is 20 CFM instead of that 50 or 60 CFM bath fan that you come in and turn on when you shower and want to run a bath fan. So when you think about it, you do the math. I can't do it in my head very well, but the numbers always land this way. Average home, 50 CFM bath fan. Say somebody uses it for 4 times a day, even 5 times a day. And when they use it, they push a button and it runs a timer, and that timer is set at 20 minutes. Sometimes they don't always push the button and it doesn't get used. So we'll just say, okay, 4 times a day, solid 20 minutes, because that button, we push it and it runs for 20 minutes, whether we want it to or not. So if we take 20 minutes times 50 cubic feet per minute, we'll get a number. And I know that's probably a pretty easy number because it's 2 times 5, but I'm not going to try and do that and speak at the same time because I'm not really that good. But bath fans with continuous ventilation need 20 CFM continuous. So that means it's 20 cubic feet every minute of 24 hours a day. And so if you do that calculation, I think you wind up with a really big number. Way bigger, like 3 to 5 times, like 5 times bigger than the 50 CFM run normally. And so what happens in these baths, we've seen these, this is kind of the backbone of really high performance building, is when you run 20 CFM in a bath, somebody comes in and showers and, maybe the mirror fogs up, and because we're running 20 CFM instead of 50 CFM or 80 CFM, the fog on the mirror might stay a little bit longer. But an hour after the 50 CFM fan would be off, the 20 CFM is still going, and it'll pull all the moisture out of that bath, which means it'll dry the shower stall, it'll dry the towels, it'll keep the building materials drier, it'll keep them from wetting because we've got constant airflow. And that bath will return back to a really nominal moisture level. in all of the carpets and fixtures and stalls, as well as the base building material of drywall, tile, and framing, and then what's in the framing cavity. That extra flow at 20 CFM is really meaningful and creates a better space for people and a much better space for the building. So finally, we'll wind up looking at the whole building and make some basic assumptions based on the normal occupancy, right? So we kind of looked at supply flow rates and what drives that, and it's people. And we looked at exhaust flow rates and what drives that, it's good sense and code. So now how do we kind of harmonize these things together? It's true that in most buildings, people need fresh air, and baths and similar rooms need exhaust flows. The same flows will manage moisture and dilute the VOCs, right? So we can do that. So the factors are near enough to each other that you can apply a common rate to a living unit. This is called the volumetric rate. So it's different from supply rate and different from exhaust rate. It's really more about volume. It can be calculated precisely to achieve the total air changes per hour. And so this is total air changes per hour. It's expressed in ACH. ACH is also how we measure leakage on building envelopes or air leakage in homes. But this ACH is different. It's air changes of hour. So if we've got a 2,000 square foot box and the box is 10 feet high, then we've got roughly a 20,000 square foot enclosure. And so the air changes to turn over that 20,000 square feet in an hour is essentially setting a fan to run that 20,000 cubic feet in that time period, either to turn over a part of an air change, right? Part of that 20,000 or all of that 20,000. And that turns into 1 ACH or 0.5 ACH or 0.3 ACH. So it's a number and it's a simple calculation. It works because we generally have more baths in North American homes, and with more baths come more exhaust flow requirements because that 20 CFM continuous starts adding up every time you add a bath. The baths have a higher flow requirement than the occupant-based supply flow requirements, you know, kind of that 15 CFM per person. And that higher exhaust flow rate and the more baths tends to push up the exhaust flow requirements higher than the supply flow. So now we've got a exhaust flow typically a little higher than supply flows. And so it lands, and they both kind of conspire to land very near a rate that is equal to 1/3 of the air changes per hour of the volume of air in the entire building. So it's known as that 0.3 ACH or 1/3 of the air volume in an hour. So just generally because we in North America, we build a lot of bathrooms and we have a relatively modest requirement for supply flows. Those things in the homes that we build, and when we look at the air volume in the homes, they just seem to kind of balance and kind of settle in around 0.3 ACH. So if we start looking at a home, if I'm creating design or part of our team's creating a design, we'll start measuring, you know, kind of how many bedrooms. That'll lead us to how many people we expect. And so when we think about people, we can apply a supply rate. Then we'll start looking at the bath quantity and mudroom and kitchen and kind of all of those exhaust areas. And we'll start pulling a value out of those areas. Those two values may be different, right? The exhaust rate could be a little bit higher. It could even be 15% higher than the supply rates, which means that if we set the overall volume at the exhaust rate, we'll get a little extra supply rate. And when we start looking at that as an overall air exchange rate in the entire volume, it's just funny how often that lands at 0.3 to 0.4 air changes per hour. And I've got some friends in the industry who say, hey, I think your supply rates are a little low. People need more oxygen coming out of COVID. We want more filtration, more air exchange. And they'll say, hey, we want to increase the supply rates and we want to increase the exhaust rates, and we want to head towards 0.5 air changes an hour, or maybe even a little bit higher. So recent work out of the last 2 years that's informing ASHRAE policy and public policy right now takes these volumes, takes these rates and really amplifies it, because when we start thinking about, things like COVID and things like that, higher airflow or higher air exchange rates are safer for us and kind of dilute any pathogens that may be present. And so part of the work is understanding kind of where the edges are, because as we start increasing the exhaust rate in some climates, like in my climate, kind of the other side of the mountains, where it gets really cold at night in the winter. And so we're not bringing in much moisture, and this kind of heads us into more of an advanced workshop. But when it's really cold in the winter and we're not bringing in much moisture, and we're pushing out the moisture that we have in the home, and we don't have enough people to contribute more moisture, the overall, that higher ventilation rate will tend to dry out the home, and we'll experience that with chapped lips and static electricity and kind of those effects. So it's a little bit of a balance, right? We're just trying to inform and understand where in the climate we are, and our potential for drying a home, our potential for managing airflow and using one of these higher airflow rates. It's all good. It's all so much better than just having a bath fan or a whole house supply fan. This allows us to even a simple system of 0.3 ACH, where it's distributing across all the bedrooms, is so much more superior, and it feels so much better than what we do with exhaust only systems. So let's start answering some questions. And we'll start looking at just kind of code minimums and code guidance. And so we'll get deeper into the calculations in more of an advanced workshop, but today we'll use this chart to start sizing our continuous ventilation system in our imaginary project. So left-hand margin, total square footage of the home. So I think I didn't even pick one, right? I'm kind of straddling two lines there. And on the top row is going to be, there we go. On the top row is the total number of bedrooms. And then below that, kind of running left to right, each line and row converge into a minimum required ventilation rate for continuous flow. And this is typical ASHRAE 62.2. So small home, well, it's not even that small, 1,500 to 3,000, 2 to 3 bedrooms, right? Those are our so we're looking at 1,500 to 3,000. That's kind of the volumetric size. And then we're looking at bedrooms. That's more of the supply and occupancy side. And we'll say 60 CFM. Okay, so that's kind of where our chart gives us. There's other answers we could come up with, but this is where we're starting. So 60 CFM continuous works for a 2,400 square foot, 3-bedroom home, because you can reasonably expect that home to be occupied by 4 people with a minimum required flow rate of 15 CFM times 4 equals our 60 CFM that it's recommending. If the home had 2 baths, the 60 CFM is higher than the 40 CFM that would be required for continuous exhaust, 20 CFM each, in the 2 baths. If it had 3 baths at 20 CFM each, it would be equal to the 20 CFM rate required for each of the 3 baths, and we'd get back up to 60 CFM. So, we're kind of covering it 2 ways, and we're looking to harmonize, and mostly we don't want to be too low. We don't want to be too high. In some cases, so upsizing is not necessarily always the great thing, but we just don't want to be too low, because we'll starve people for oxygen, or we won't just have enough exhaust to manage the moisture. These ASHRAE charts are easy way to meet the code requirements for balanced ventilation system. They're a good starting point because they will provide the reasonable flows that create healthy space for occupants. We can make them even more comfortable and efficient by adding heat and energy recovery, as we talk about maybe in a more advanced workshop. Essentially, when we start doing a high performance project, we probably wouldn't use this chart and say we're in a 2,400 square foot home with 3 beds. So it could be a few different things going on here, but if you look at the exhaust rates, which will probably kind of drive it, 3-bedroom home might have 3 bathrooms. That's pretty reasonable. So 20 and 20 and 20 might actually have 3 baths and a powder. So if there's a powder, we could put another 12 or 20 in there. It's a powder, so we might want to stay with 20 because it's considered maybe a bath. We haven't put anything in the kitchen yet. So we're 20, 20, 20. And then if we add a powder, now we're another 20. Say that's 80. And then, you know, we've got a kitchen. Kitchen's a source of moisture. It's a source of cooking smells. We've got a range hood, but maybe we don't always turn it on. And we've got a ventilation system. So if we run some ducting into the kitchen and we give that, our practice is maybe, you know, as we give a kitchen something around 30 CFM. So, you know, we're 80 CFM plus 30 CFM. Now we're at 110 CFM. And 110 CFM in a 2,400 square foot home, all those bedrooms are getting steady flow rates. So they're getting really good continuous fresh air. The bathrooms are all getting continuous exhaust, so they're going to stay in really good shape. The kitchen's going to, you know, the experience in the kitchen is going to be really fresh and clean because we've got 30 CFM. That's 30 cubic feet every minute coming out of that. We're not hitting an energy penalty because as we pull that 110 CFM out of the home, we're replacing it with fresh 110 CFM across a filter and then running through a heat exchanger. And the heat exchangers that we have available in the market across the broad spectrum of the market, the worst ones are maybe 50%. So if it's a 50% efficiency recovery, then we're losing about 50% of the heating energy or the cooling energy that we put in the home just to that 110 CFM. And that's a number, and that's Title 24 calculates that number, and that kind of informs why we use HRVs across and what the effects are across all the climates that we work in. If we can get an HRV that's 90% effective, now we're only losing 10% of that conditioned energy, which then means we just don't need as big of a system kind of creating the heating and cooling in that home because we're retaining it, and we're retaining it without losing it, and we're keeping this home in with really fresh, consistent air. And so that's a really nice way to set up a system. So any questions about this particular chapter? We're actually kind of getting into the closing slides. So if we kind of want to take a deeper dive into kind of how to size the system or any other points, we're almost an hour and a half in, and we're coming up to our closing slide. Okay, a couple of questions. Thanks, Edward. I like getting questions that happen to work. Okay. Edward's asking, are ERVs more expensive, including maintenance, that much more expensive than an HRV? Maintenance, no. Initial cost, depending on the quality of ERV, yes. So ERVs, we'll spend a little moment here. ERVs are, I'll start with HRVs. They're the simple. HRV is heat recovery ventilation. So if we say we have a building and it's heated to 70 degrees And at 70 degrees, we're pulling out 100 CFM of 70-degree air, and we're bringing in 100 CFM of, let's say, 30-degree air, because it's really, really pretty simple. The difference, so it's 30 degrees outside, 70 degrees inside. And so essentially we want to retain as much of the energy associated with that 70-degree maintenance as we can inside. So there's a delta T. It's the difference between 70 and 30. So that's 40 degrees. And at 50% recovery, essentially what's going to happen is the airflow coming out will pass, that 70-degree air will pass across a heat exchanger, while at the same time, the 30-degree air coming in will pass on the other side of that heat exchanger. Heat recovery is basically nature's resistance and insistence on always seeking a balance, right? So on the leaving air, you've got a high concentration of heat, and on the entering air, you have a low concentration of heat, and it's like a radiator. So the high concentration of heat is going to seek to warm the lower concentration of heat. And the industry has gotten really good at kind of making these heat exchangers where maybe the most basic will be 50%. So 50% of the energy will make it from the 70 side and make it on the 30 side. So the difference is 40. So that means essentially what we're going to do is we're going to see the incoming temperature after the heat exchanger of that 30-degree air. 50% of the delta T is going to land on that incoming air. So the incoming air into the building won't be 30, it'll be 50. For me, that is not great. I don't really like 50%, but from an energy standpoint, okay, we're losing half, because if we didn't have a heat exchanger, 70 would be leaving, 30 be coming in, and we would just be pumping out all that heating energy that we asked our furnace to make, and we just lose it, right? So at 50%, we're getting 50% back. At 90%, if we take 40 degrees times 90%, we'll get about 36 degrees or 35 degrees. We'll make it a simple number. It's in there, and I can't do math while I'm talking or presenting, so I'm not going to try. But we take 30 and then add another 35, even if we added just 30, right? And that's kind of low on a 90% recovery. So now we've got 60-degree air coming in. We got 70 leaving, 60 coming in. And so we're just missing, maybe 10 degrees, and we'll have to reheat the inside that 10 degrees to make up that loss. So if we can get it a little higher, then we lose a little less energy. So that's heat recovery. Energy recovery is a little bit different. Say we're in Atlanta, Georgia. It's an extreme condition. So in Atlanta, Georgia, in the summer, it's very much a cooling environment, and it's also very, very humid. And so we got lots of moisture outside. And what we don't want to do is bring in that heat. So it's the same as that kind of heat recovery in reverse, because now the heat's on the outside instead of the inside, but it works the same. So we set up a heat exchanger that essentially we can bring in that 96-degree air, and we've cooled the inside of the building down to 70, is just as a discussion point. And we do a heat exchanger so that we're not bringing in that 96-degree air into our building. But the other thing about that air in Atlanta, Georgia, is it's really full of a lot of moisture, right? It's really, really high humidity. And that high humidity, if we bring that into our building, that's really going to drive up our humidity loads inside and kind of create a problem. So that's what an ERV does. So Edward is asking the question saying, hey, if I put in an ERV because I'm in San Diego and I'm on the coast and I want to leave some of that moisture outside, so I'll put in an ERV. And the ERV will basically do the same thing as an HRV. It'll bring in the moisture and the heat energy and then send it across the heat exchanger and send it back outside. And so, Edward, ERVs are more expensive generally, especially the better you get and the better performance, because they're trying to do two things, right? A heat exchanger is just kind of like a simple plate heat exchanger. you heat one side and that heat transfers over to the other side. And it's just heat, right? So it could be solid material, and you're just looking for material that won't build up bacteria because your airflow is passing over it. And it's kind of, it's solid and dense so that it can accept energy and pass it through it. But moisture is different in that you kind of need like a Gore-Tex material. And the Gore-Tex material, the characteristic we're looking for is we load one side with moisture, and that moisture transfers over to the other side. So when we run an airflow by it, we pick up some of that moisture and put it back or send it back in the direction that it came from. But that material that does that doesn't have the density that a flat plate heat exchanger would have. So we kind of suffer a little bit on the heat recovery side in order to get the moisture recovery side. So it takes a much more advanced material to kind of create that relationship, and they exist. We work with them. And so, yeah, essentially they can cost anywhere from, 15 to 10 to 15% more than an HRV, maybe a little higher depending on whose it is. Maintenance, same, no difference in maintenance. It's all just first cost. And heat exchangers are a great way to manage moisture. If you're building in Tahoe, you want an ERV. If you're building in the Bay Area and you're not on the coast, you probably want an HRV. And as a company, the reason I say ventilation is really kind of a team sport is it takes a good partner to kind of look at where the project is, understand what the climate is and the type of project and the occupancy and so forth, because it's not just one rule and one map, even though maps that kind of say HRV territory and ERV territory exist. It's, if you really want to get down to it, it's really intentional and really want to understand kind of where the sites are. It's hard for me to see your other two questions because the print on my side. Okay, same question. Yeah, no worries. Good. So hopefully that's a very brief kind of discussion between ERVs and HRVs. And ERVs, on HRVs, we're managing thermal energy, and on ERVs, we're managing thermal energy and moisture because we exist across all these different climate zones. There's different moisture loads. And if we're up in the mountains or in a high desert situation, there's very little moisture. So it's all about kind of keeping the moisture in the building rather than just sending it out by fan power. And in other areas like the one I'm in today, or more kind of moderate climate zones, Napa, things like that, many places, it's really just managing the energy. And the funny thing is I'm talking to you from a cloudy, rainy day. Temperatures are only in the 50s, but often we get in the 40s. And when it's rainy here in the Pacific Northwest in the 40s, it's like really high humidity outside, because it's raining, right? It's in liquid form. So it's cold and raining. And the funny thing is, you bring that 40-degree high humidity moisture into a building across a heat exchanger. And essentially what happens is that air heats up and it goes from high humidity level or high relative humidity. And as you heat it up, the water molecules kind of disperse and the air becomes a larger volume, and the humidity drops down, or the humidity of the airflow drops down to around 50%, which is just ideal. And it's kind of right in that optimum range. So it's funny, in this area, we're very much HRV. In high mountains, it's ERV because there's not a lot of moisture coming in. And the extreme case is, I can't tell you how many projects I've seen that are mountainous with 2 retired adults and nobody else in 3 or 4 or 5,000 square feet, right? 2 people in a big box in a region that over the winter has no moisture coming in, and 2 people don't make much moisture, and that moisture is going to disperse across this big box. You definitely need to manage moisture. That's why you need an ERV in that case. And you probably need to add dehumidification into the building because there's just no way to keep enough moisture to keep that space feeling comfortable. all of these things we can do with ventilation. It's really simple, it's not complicated, and it yields a really nice effect on the occupants, much more than the finishes, right? These are things that help us thrive and be healthy, and the next occupants that experience that building also get that same health and that ongoing benefit instead of picking a new paint color. So great things about ventilation. You can totally nerd out on it, and I think I'm kind of at the end unless there's more questions, and hopefully this was helpful for people.
Thank
And
you.
so, yeah, I might hand this back to you now with your guidance.
Yeah, thank you so much, Albert. That was a super informative training. I feel like I learned a lot today too about ventilation. So thank you for that. Just a closing slide. If you have any questions regarding AIA available units for architects, we have those available, or any questions related to 3CRN, please feel free to email me. I'll drop my email on the chat. And coming to you are slides, the recording of this training today, and a survey. It should be sent out in the next 2 days, so look out for that in your inbox. And then these are some of our upcoming courses that we have. I'll drop our calendar into the chat as well, so you all could look at the trainings. There's a lot coming up. We have our high performance fundamentals series going on right now. Tomorrow we have our third course, which will be on enclosures, roof, walls, and floors. So that series has been really awesome to have. And then next up, we have the fourth class of that, which is about heat pump fundamentals, space conditioning, and water heating. So yeah, take a look at that. But with that being said, thank you so much. I'll hand it back to Albert if you want to say anything else, but we really appreciated you being here today.
Well, thanks. It's always a pleasure to work with 3C Ren and just help people kind of build better buildings that are better for the occupants, better for us, and just kind of keep the progress moving. So if we can help you some way, always a pleasure to hear from folks and reach out to Small Planet Supply. And I hope everybody has a great day.
Thank you so much. Bye, everyone.